So let's do the moment of inertia of a compound structure. So if I have a disk here rotating about its center, and then I have a rod sticking out of it like that, the rod is this length right here. It is somehow magically attached there, so it does not fall off. I have a radius here of, we'll just say 0.4 meters, a length here of, make it 0.3 meters. The mass of this, mass of the rod is, make it 0.1 kilograms, and mass of disk 0.2 kilograms. So the moment of inertia of the structure, assuming it's rotating, if that's my axis, so it's rotating around like that, my moment of inertia is equal to, well, ultimately it's just a giant sum. So this is the moment of inertia of the disk plus the moment of inertia of the rod. The disk is spinning about its center, so this is the moment of inertia of the disk about its center of mass. The rod is not, so this is the moment of inertia of the rod about its center of mass, plus, using parallel axis theorem, m mass of rod times d squared. So this is 1/2 mass of disk times radius of disk squared, plus 1/12 mass of rod times length of rod squared, plus mass of rod times the distance the axis moved. The axis moved from here to here, the center. So this would be radius of disk plus 1/2 length of rod squared. And probably easier to plug in numbers at this point. So this becomes 1/2 times 0.2 times 0.4 squared plus 1/12 times 0.1 times 0.3 squared plus mass of rod 0.1 times radius of disk 0.4 plus 0.15 squared. And pulling out the trusted calculator, we end up with, so 0.5, 0.2 times, 0.16 times, so this is 0.016. 12 reciprocal, 0.1 times 0.09, 0.00075 plus 0.1 enter 0.55 squared times 0.03025. So notice that the biggest contribution is this piece right here. If I add them together, I get 0.047. Now we haven't talked about units yet, so this is just as good a time as any. The units of this would be, well, it's a mass times a distance squared, and it's kilograms times meter squared, so this is a kilogram meter squared. There is no single unit for it, so you just deal with it as is. So that is the moment of inertia of this. If I then change the problem slightly to suppose it spins twice as fast, what's the new moment of inertia? Well, it's a trick question because the moment of inertia depends upon the geometric structure, doesn't depend upon what it's actually doing, other than as long as the axis stays the same, we are good. So that is the moment of inertia regardless of how fast it's spinning about that same axis. Now, if I shifted the axis to here, then the disk suddenly becomes much more dominant, and that I think you can figure out.